Sir, yeah, live start.
Yeah.
Thank you.
Hello everyone. Are there any students here?
Hello.
Hello.
Yes, sir. You're audible, sir.
Yes. Is this a student?
Yes, sir. Sir, from the online course. I'm taking it as exam for exam also.
Oh, wonderful. Wonderful to hear that. So, may I know your name and where are you from?
Sir, I am a PhD candidate from IIC Bangalore. My name is Himanshu Krishnani, and I'm in aerospace engineering department. I did my masters in NIT Allahabad, and I did this level set method for interfacial flow tracking. I'm taking this course as an add-on to my master's knowledge.
Okay, very, very nice to hear that, Himanshu. So, what I can do is there are two ways to do this. I could actually open the NPTEL. I have the notes with me, OneNote notes. We could do that, or you could start asking any questions if you have.
Sir, one question I posted through forum, and one
Yes.
question I posted in the announcement, the discussion forum. One is.
So the plan is basically for us to take up those questions. Can we, for the sake of this I believe will be live streamed, which means that it gets recorded. For the sake of benefit of people who are basically who will be watching this offline, it will be good for you to post the question again, and then we will see how I'll try to answer the question. Can you just start asking the question again?
Yeah, I should I type this in the chat?
No, you can just ask the question.
Sir, my question is regarding the non-dimensional number. First is so I went through some papers, and every paper I see like a flow in a confinement, like a bubble rise in a confinement, highlights that there's a different kind of, so they wrote a different kind of Reynolds number, and unconfined flow wrote a different formula. So I'm confused about how these non-dimensional numbers are quantified so in these bubble rise problem we were tackling. So how do we quantify the Reynolds number, and what do we say the characteristic length in the dimensions are?
Okay, so I think Himanshu, let me just rephrase the question again. So the question is about how do we pick the typical characteristic scales when we write down non-dimensional numbers. So as a case in point, let's look at, let's say, Reynolds number. A Reynolds number has a density parameter, then it has velocity, then it has a length scale, and it has viscosity. Okay, let's consider. I want you to imagine a problem. It will be good to have a small piece of paper next to you. I want to imagine a problem where, let's say, we are talking about a bubble that is rising through a fluid. Okay, let's say an air bubble that is rising in water. It could be an oil bubble that is also rising in water. Okay, the discussion equally is valid for a water droplet settling down in oil. Okay, or a raindrop that is falling down in air. Okay, so in all these problems, as you can see, I'm taking a more complex situation, more than what you actually talk about. You talk about confinement as well. We'll come to that. So if you look at all these problems, you can clearly see that there's two phases. So there's two densities, two viscosities, and the characteristic velocity in this case is the bubble rising speed. Okay, that's the characteristic speed, assuming that the surrounding fluid is quiescent. Okay, if the surrounding fluid is also moving and the bubble is rising through a moving fluid, then one of the characteristic scales that you can choose is relative velocity. Okay, now and then of course there are several length scales that come up. For example, if you're talking about a bubble that is rising in an unbounded region, unbounded domain, then a typical characteristic length scale is a bubble diameter. Now again, you have to keep in mind that when we talk about bubble diameter, and we actually do an experiment or a simulation of this problem, you'll see that the bubble never remains perfectly spherical, correct? So it tends to deform. So then you can ask, what is the bubble diameter? I mean, you can say, well, diameter as an idea is only for a sphere. What if it's deformed? So now there are several ways I think you can define. You can say in your simulation that could be an initial condition in a simulation or an experiment, or you could say I know the volume of the bubble. Okay, even when it deforms, the volume is not going anywhere. The volume is conserved. Therefore, I can come up with an equivalent diameter. Correct. So that's one aspect. Then the next aspect is about confinement. Let's say your bubble is rising through a confinement. Now, when you define Reynolds number is a measure of inertia to viscous forces. Now, it's really question is about what kind of inertia are you looking at? If you're looking at inertia at the scale of the entire experiment, then the characteristic scale would be the confinement, sort of the scale of confinement. Okay, let's say bubble is rising through a channel. Okay, but you can also have another Reynolds number which is based on the bubble. Okay, you can actually define two Reynolds numbers, or you can say I'm going to define only one Reynolds number and an aspect ratio. Okay, which is or a size ratio. Size ratio is what is the size of the bubble to the confinement. Is this clear? So there isn't anything like a unique way to do this. Okay, but what you have to keep in mind is that there is an element of convention in this. But what you have to keep in mind is that once you have followed a system of non-dimensionalization, okay, then you have to if you're comparing your results with somebody else, then the way you've non-dimensionalized your numbers have to match. Correct. Example, there is no reason for the characteristic scale to be the diameter. It could even be the radius. So when you compare it with somebody else, you have to keep in mind that if somebody else is using radius and you're using diameter, then you have to remember that your Reynolds number is going to be double the value that they have used. Okay. So, but if you remember your Buckingham Pi theorem, then what you will learn first of all is how many unique non-dimensional numbers can you define. What are the most independent number? How many independent non-dimensional numbers you can define? So once you have defined those non-dimensional numbers, then you can define any new non-dimensional number in terms of the ones that you have. Okay. Now, the final part that I want to sort of say is how do you pick the right kind of non-dimensional numbers? Okay. Now, how do you pick the right kind of non-dimensional numbers? That depends on what is the dominant physics in your problem. If you're if you're looking at a problem which is dominated by inertia and viscous forces, meaning inertia is let's say is the dominant force and viscous forces is the retarding force, then a relevant non-dimensional number could be the ratio of inertia to viscous forces. But if you are looking at a problem where you're looking at inertia is a and inertia, there's a balance between inertia and surface tension, then the dominant non-dimensional number will be a balance of inertia to surface tension. Okay, this would, for example, be raindrops that are falling. Okay, because in raindrops that are falling, there's inertia, there's gravity, and surface tension. Okay, the viscous forces, the speed at which the drops are falling, the viscous forces are not that important. Okay, at least, and so I'm not necessarily, I'm not saying that it's absolutely not important. It is of course what is giving the raindrop some kind of a terminal speed. That is what is slowing down. But more relevant non-dimensional number, especially as the droplets become very small, it will be inertia to surface tension. That would be the Weber number. Okay. So I've sort of given you a very broad explanation. There isn't a perfect, unique way to do a non-dimensionalization. But I like to personally think about non-dimensionalization in terms of dominant forces. Once you understand the dominant forces, the ratio of the dominant forces will give you the ratio of the forces will give you a non-dimensional number. Himanshu, does that partly answer your question?
Yes, sir. Yes, sir. It actually it bears this fact that it is not a unique way. That is why we are seeing different kinds of representations.
Yes. Yes, yes. So there isn't a unique way. In fact, another thing that you have to keep in mind is that there are numbers which basically which have um, which have different names for the same kind of quantity. For example, well, I can. I mean, I'll give you in bubble dynamics. For example, rising and falling. Okay, you have numbers like Galilei number. You have Eto's number. Okay. Now these numbers are, you will see if you start looking at them closely by rescaling the length scale or to choosing a different, slightly different length scale or a velocity scale, you'll see that they sort of reduce to what you conventionally have learned about Reynolds number, Weber number, and so on. Okay. But one thing is absolutely important. When you compare results, your results with somebody else, it's very important to make sure that your results and their results, I mean their work and your work have the same non-dimensionalization, meaning the same characteristic length scale, velocity scale, and so on. Otherwise, you'll be comparing wrong things, and your result may not match. Okay, you want to?
Yes, sir, it is clear, sir.
Okay, you also had another question.
Sir, one question I posted in the discussion forum. I want to ask that.
Yes, please, absolutely.
So there in like in video in in week one, lecture two, you when you wrote the equations for the continuity. So the continuity equation you wrote was it was between water and air. So you wrote divergence of air and divergence of velocity of air equals to zero. The incompressibility condition in air. And then you wrote divergence of velocity W, VW is zero, and sir, that was, I mean, it is, so in Navier-Stokes, it makes sense because we have two different properties of fluid. But in when we are saying the incompressibility condition, then why do we have to write a subscript A and W?
So you are referring to which particular lecture in week? Can you again refer to which lecture?
Uh,
This is the jump conditions that I had written down. I derived, correct?
yes, sir, it is there, sir.
This is the jump conditions at an interface, right?
Yes, sir.
Okay. So when we derive the jump conditions at an interface, let's basically again there are two broad jump conditions that we derived. One is basically based on mass balance, other is based on momentum balance. Correct? Hmm?
Yes, sir. Yes.
So let me again, I'm just trying to make sure that I understand your question correctly. The question was, why do we have two different? Can you just repeat the last bit again, please?
Sir, when you were writing the incompressibility condition, you wrote subscript A and subscript W. So divergence of VW and divergence of VA you wrote in that. So in water and air, sir, I have I can can I tell the video number?
Yes, yes, yes.
Just sir, it can be seen at video number 2 at 7 minutes 49 seconds. There you have written interfacial close. Unit
Okay,
3,
okay.
Unit
Yeah, I
3
see
week.
that. Okay, so I have. Let me just. Uh, can you actually see my screen, or what do you currently see?
We see the camera view, sir.
Okay, so let me see if I can um, share this particular thing. Okay, let me just see. Hold on. I'll share the screen and So Himanshu, can you see? Is this the one that you're referring to?
Yes, sir. Yes, sir. Here it is written, sir.
Okay, perfect. Okay, so again, so now I have two. I have air as a standard, common interfacial problem that we encounter typically between air and water, and I'm showing you some kind of a wavy structure on the surface of water. So we know that both the fluids, air and water, individually are incompressible. Okay, which means that I'm writing down the continuity equation and Navier-Stokes equation, the incompressible Navier-Stokes equation for both the fluids separately. That part there is no. I hope there is no doubt about that. Correct?
No, sir. No doubt.
Okay.
But
So now, okay. Then
but sir, why refer to it as subscript? Because it is a field. It is a velocity field. So it would be at both sides. When sir, actually when we were solving this in numerically, so
okay.
we had only one pressure Poisson equation. So
Okay, I understand. Okay, so there are several ways to attempt to solve this. Okay, there is. I can now see why this question has come from. I'm trying to understand where you're coming from. So let's say if you're let's try and basically think about different ways in which you can try and solve this equation. If you can solve it. Now, if you have air and water separately, there are two distinct phases. I can basically solve for the air above and solve for the fluid below, but provided I can apply a boundary condition for the air on the upper side and also air on the lower side. Let's say air is on the upper phase, correct? So the air phase, for example, let's say goes from the surface of water all the way to infinity, or maybe there is a wall that is not shown here. Okay, so you can clearly apply conditions on the upper wall. That part is clear. I mean, you would apply standard no slip and no penetration conditions on the upper wall. The same thing you could do it for water. Okay, so either you have the water level all the way goes to infinity, or the water basically depends on the geometry of the problem. You could have a wall. That depends on the nature of the problem that you're trying to solve. But you cannot complete the solution of both water and air on their own, because there is an unknown boundary, which is the position of the interface. The position of the interface can be thought of. It does two things. One, it tells you what is the domain of the air and what is the domain of the water. Okay, I'm using the word domain because this is a word that people who do numerics also use it. Okay, you have separate regions for air and water. What are the domains, individual domains? So it means that you have to, and this is a domain that can evolve with time. Okay, so it means that the momentum equation and the mass balance equation of the air is coupled to the momentum mass balance equation of the water. You can write down separate equations along with an equation for the interface. Okay, this equation for the interface is where all these jump conditions come in. Okay, which is what is being discussed. Okay, in subsequent lectures. So the entire section, subsequent discussion below this is about deriving those conditions for the interface in the middle. So the conditions of the middle, you have to basically say, look, I have to determine its position. B, I have to basically find out are there any tangential forces that are getting transmitted across this interface? Are there any normal forces that are getting transmitted across the interface? So there are these class of solvers, okay, called, let's say, free surface solvers. In free surface solvers, typically what you say is that the gas is passive. You don't basically solve for air at all, okay, but you say that the air above has a constant pressure, okay, but you let the boundary evolve with time, okay. Then you have these other class of numerical solvers where you say that I will explicitly solve for the air and the water. Okay, and I will apply the normal standard stress balance at the and the kinematic condition. Kinematic condition is which basically relates the velocity of the both the fluids to the position of the interface. I can actually explicitly write and develop a solver where with a moving boundary. These are moving boundary solvers. Okay. Now, of course, in these moving boundary solvers, what you typically do is you would have a separate grid, numerical grid for the air, separate numerical grid for the water, and you will need a you need an interface. You'll need to identify the position of the interface where the air and water are moving, which really means as soon as the interface moves, you have to imagine that, I mean, the one way to do this is that the grid in both the fluids will deform. Okay, you can also have more complicated situations, and I'm not a numerical expert on these matters, but you can also have a complicated situation where you have overlaying of grids. Okay, one grid is basically tracking the interface alone, on which the interface is moving, but then you solve the momentum equation on a different grid. Okay, but there is another alternate way of doing this, where you say that you think of air and water as not distinct phases, but as part of one continuous phase. Okay, and the only thing that distinguishes water from air are the material parameters. Okay, that is density of air, density of water, viscosity of air, and viscosity of water. So if you look at a system like this that you're seeing on the screen, and we know, and as discussed in the earlier lecture, was that you know that there is a very sharp transition from air to water. So sharp that practically you can think of it as a step function. Okay. But from a numerical standpoint, it is very difficult to implement a step function. Okay, because it's a discontinuity, and numerical solvers tend to have difficulty in dealing with this sharp sudden change. So you say, well, okay, I don't want a sudden change, but I will allow it's acceptable for me that I have a sharp change. One of the simplest ways in which you can have a sharp change is basically have I think I discussed this earlier. Let me just pull that out so that I'll show it to you. Just give me a second. Yeah, sorry, it was in this third one. So one way you can actually have a sharp change, and I hope you can see this, is basically say that there is a sharp change between air and water, but in reality, the thickness may be the change over which you transition from air to water may be only angstroms, meaning it is basically much below any numerical capability of any numerical solver, continuum numerical solver. But you say that it is okay for me to sort of smoothen this out, okay, a little bit more. So you typically, if you put a few grid cells across which it will change, in a volume of fluid cell method, for example, as one of the standard ways in which people, a popular method, I wouldn't say standard, it's a popular technique to solve for interfacial flaws. You say that there is a interfacial cell where the interface is passing through, and the interfacial cell is where a cell which has a little bit of water and a little bit of air. So they use this, it's called volume of fluid, because there is you're tracking the volume fraction. If the wall if you are completely in water, then the volume fraction is 1. If you're completely in air, the volume fraction is 0. But somewhere in the middle, if you are at the interface, then the volume fraction is between 0 and 1. Okay. There are other ways of doing it. Level set technique is another technique. So in such methods, what you essentially do is you reduce this problem not to basically not to two different distinct phases, but one continuous phase. Okay, one continuous phase. But again, in those methods, that you're simplified the problem because you don't now need a moving grid and all that. Okay, you can work with a single grid which spans across both the fluids. You don't have to think of them as two different velocity fields, two different pressure fields, two different density fields. You just think of it as a continuously evolving thing. But the challenge comes in basically implementing these additional forces like surface tension. Okay, how do you incorporate surface tension? If it's a single phase flow, then there is no surface tension. Correct. There is no surface tension between salt water and sugar water, salt water and fresh water, because it's miscible. Okay, but if you but salt water and fresh water are miscible. But let's say what about oil and water? There is a very sharp transition, and what you normally do is in such cases, you will you in these kinds of methods you will miss out surface tension force. So what you then do is you say, well, I've missed out surface tension force, but I know the boundary where there is a very sharp transition between water and air, okay, or an interfacial cell, okay, or where this volume of fraction parameter or level set parameters rapidly changing. And at those cells, you add an additional force. That additional force is the surface tension force. Okay, but you add that additional force only for those cells. Okay, so you actually apply it like a body force term, but only for those cells. So it essentially becomes like a surface force. Okay, so hopefully I've explained the differences between the approaches. Strictly speaking, these are two different fluids. Did you get that, Himanshu?
Yes, sir, I get that, sir, because yes, sir, I remember that we are smoothing out the interface in the numerical also, like we are using Brackbill's surface tension model.
Absolutely. So what you're when you basically do that, you are adding the force directly to the momentum equation because you don't have separate jump conditions where you can incorporate surface tension. Okay, and therefore the only way you can actually add surface tension is to the momentum equation itself. But you don't add surface tension to every cell in your domain. You only add it to the interfacial cell.
Yes, sir. Yes, sir. We are using this direct delta to.
Dirac delta. Dirac delta essentially says that it tells you where that quantity is non-zero, and it also, if you are away from the interfacial cell, that term is zero.
Yes, sir. It clears my doubt.
Yeah. But strictly speaking, theoretically, these are two distinct phases. That's the way to basically numerically solve. And the approach that you are referring to is to simplify the numerical complexity in a problem. Yeah. I'm happy to take any other questions.
If I could ask one from numerical scheme that we have, we have worked out some simulation and we have found some interesting result that I wanted to ask about.
Yes,
And,
okay. I can let me just put a disclaimer out. I'm not an expert on numerics, but I'll tell you whatever I understand.
sir, this solver we have validated, and so what we did was that when you said in the first week that it is what we are doing is that we are seeing that we could observe jump because of density difference. So what we did was that without including the surface tension, and we did not allow the second phase to advect, and we held that stationary, and we gave a density jump, only the density jump and the viscosity jump. The two properties of two fluids are different, but we have not given the interfacial force, the surface tension. And then we saw that the solution evolved to have some vortices on the surface itself. And I have this picture. I'll post this on discussion forum also. And can I send on discussion forum?
Absolutely, send it to me. Huh?
So, sir, I'm sharing this now.
Or you can send it to my email also.
Yes.
If you think it's too far away from the course, okay, then please you feel free to share it to my email as well.
Yes, sir. So
Yeah, I mean you
yes.
can just search my name on Google. You should be able to get my email address.
Sir, give me 1 minute. Can I send right now, or should I
Yes,
send
yes.
later?
You can send it right now also. I'm in front of the computer.
I'm sending this GIF, sir, GIF that we have created.
Yes, okay. You're sending it via email now?
Yes, sir. Yes, I'll send on email. Otherwise, my discussion
You still
forum is open only, so uh, I can post there also.
no, you post it in my email first.
Yes, sir. Yes, sir.
I haven't received anything yet. There's also another student in the discussion today, Sai Krishna. Hello.
Sir, I'm sending 1 minute.
Yeah.
Sir, I have sent one PNG file. So
I'm just looking at. Give me a minute. I still haven't received it. Yes, I received it in Manchu. Okay, so I can see some kind of a droplet or something like this. Correct?
yes, sir. Yes, sir.
I believe this is okay. Let's basically understand what is it that you're trying to show me. Um, let me. This tool is. I'm trying to.
Sir, what we did here?
Is this what you see now?
Yes, sir.
Do you
Yes, sir.
see the? Um, okay, so you should be able to see the whole on the screen. You should be able to see the picture. Okay. So all right. So what exactly have you done here?
Sir, what we did was we had this we are using this single fluid approach in which we are using this heaviside function for switching between the densities. So the two densities are the density of the droplet and the density of the surrounding fluid, and it is inside a confinement. So this is a closed box. We have validated lateral vein cavity over this, and what we did was we ran the solution without advecting this second phase. So without advecting the second phase, when we ran the solution, it gave us the streamlines evolved, and these are significant. I mean, these are significant values in term the quantity is significant. So the values are not.
Yeah, I got it. So I'm just trying to understand what is you have a box, you have a droplet which is not exactly at the center of the box as I can see, or is it? Are we at the center of the box?
Yes, sir. It is at the center of the box.
It's okay. The droplet is in the center of the box. Where how are you driving the flow?
Sir, we are just giving neighbors. We have used the simple algorithm we have used for
No.
incompressible.
What I mean is that, okay, I'm asking even more basic questions. You have a droplet of a different density than the surrounding fluid. The droplet is basically colored in some shade of blue that I can see here, the circular droplet. I'm guessing this is a two-dimensional simulation. Okay, and you don't have gravity, which is what is preventing, which is basically allowing the droplet to stay in place. Correct?
Yes, sir.
And you probably have a single numerical grid in the entire domain. Okay,
Yes, sir. Yes, sir.
and so the only difference is that when you're inside the droplet, you have a different density. When you're outside the droplet, you have a different density.
Yes, sir.
Okay,
Yes.
and perhaps the same for viscosity.
Yes, sir. Yes.
Okay, now I can see a flow that is generated. Well, what are the boundary conditions for this problem? The boundary conditions for the outside, is it? This is a lid driven cavity. So is the upper boundary moving to the right? Is that what it is, or what? I don't understand that.
Sir, it was a literal cavity solver only, but we stopped the top surface from moving. So top surface is not, but it is just the solution is evolving without we giving any external.
Okay. Just the static system. You're trying to evolve this. You're trying to just see what is happening, and it's just a static system.
Yes, sir. Yes, sir.
Okay. So, but you basically said these velocities are significant. What do you mean by how do you how do you determine that this is significant?
Sir, it was some point one value. So it was in the magnitude. It was coming out to be point one. Sir, at these so this maximum value was coming out to be point one, and I'm I'm using the dimensional formulation in which I use meter per second like that. So it is coming out to be very, very big value. I have this. I mean this result and GIF also how it evolves and but this is the last step. So
So this is so. Um, uh, okay, I can only guess what is probably happening. Okay, this is purely a guess. Okay, what I think will happen is you have a Cartesian grid. Okay, and you are putting a circle over the Cartesian grid. So the Cartesian grid will never perfectly match the circle. So if you actually zoom into the edge of the droplet, you may see some kind of a staircase pattern. Okay. Of course, there are ways to improve that, where you say it's not a staircase, but it's basically like the circle can be represented like a polygon. Okay. So now what ends up happening is if you every time step, you basically, even if there is a small variation in the position of the droplet, if it's is there surface tension in the problem?
no surface tension in the problem.
There is no surface tension in the problem. So I personally think this is just a I'm guessing. If you This is just a random velocity field that is generated, okay, and the random velocity field that the moment you have a, let's say, a lid that is moving at the top, this velocity field will disappear, okay, and I suspect that's my suspicion, okay, and I say this because if the droplet, think about a droplet that is there in the middle. If that wobbles a little bit here and there, and why should it wobble? Because every time you're basically computing the position of the droplet, even though you're fixing it in space. Okay, it is not a perfect circle. Okay, there is always going to be small fluctuations to the circle, and the very fact that it is not it itself cannot be a perfect circle because you are overlaying it on a Cartesian grid. And therefore, what I suspect is, let us say the circle is slightly biased more to the left than the right, or from the bottom more to the bottom than the top, even by one cell or half a cell, or half a grid cell. Then there is a mismatch in the momentum and the mass balance across that cell, and that is there primarily it's a mass balance that is mismatched, and that is what will drive currents like this. So this is just random currents. For example, you take a standard volume of fluid solver. Okay, in a volume of fluid solver, you actually put a droplet. Okay, and you leave the droplet, and there is no gravity. There's nothing. Now, if the solver is not very accurate, meaning the interface tracking is not very accurate, you leave the droplet right there in the middle. Then what is likely to happen is the droplet, after a long interval of time, the droplet will basically start doing the random work, but over a very long period of time. This is what will happen even if you allow this droplet to move around. It will exhibit a random walk. It will exhibit a random walk. This is all my suspicion. Okay. If it will exhibit a random walk, I suspect it will exhibit a random walk because the velocity field that is generated is because of tiny numerical errors that are generated in the solver. Okay. But the moment you put a bias in the system, for example, if you let the droplet, let's say, settle down because of gravity, or if you basically put a flow that is driving the flow, then all these currents will disappear. Okay. So right now you don't have a way to say whether this is large or small, because you only have one velocity, and with one, in general, you can never say something is large or small unless you have a reference to compare it with.
Yes, sir. I understand, sir.
Okay. So my suspicion is that if you were to do a volume of fluid or a lid-driven cavity, I mean, a level set problem where you let this droplet, if you don't freeze the droplet there in place, but you let it evolve with time, but you don't give any external velocity field, my suspicion is that it will exhibit a small wobble here and there, and that wobble will be like a random walk.
Yes, sir. I understand. Yes, in the later simulations when we let it evolve, it was rising perfectly well, and there was no problem after that.
Because
When
you have
we
given a bias. The moment you give a bias, you let's say if you let's say this the droplet has a low, and the droplet or the circle that you have here has, let's say, a lower density to the surroundings, it will rise up by gravity. And the moment you have rise up by gravity, then you clearly there is a that bias will overtake all these kind of tiny numerical errors. So they will not appear at all.
Yes, sir. I get it, sir. I get it. Right. It's clear now.
Hmm. Okay. Any other questions?
Not from my side, sir. I clear every question.
Okay. So we will. The plan is to sort of do this every week. I can see today we don't have any students, but I hope some of the students will get to watch this, and I believe the NPTEL office will post this on the channel. And please, I encourage more students to come. It's close to 12, so the plan is roughly between 11 to 12. We will have this kind of a weekly session, and please tell me, please raise any doubts that you have, and so on. Okay.
Sir, is it okay to email you or put on discussion forum?
You can put it on the discussion forum.
Okay, sir.
Yeah. And of course, we'll take it up again in the, if you have a doubt, we'll take it up in the discussion. If you, because we're going to have this weekly thing, you raise the question. I want other students who also can see the question to also, it should also pique their curiosity. And then we'll take up the discussion in the discussion forum every Saturday at 11 o'clock in the morning. Okay. All right. So thanks to I see only Himanshu right now. So thank you, Himanshu, and I'll see you again next week. All right.
Thank you.
See you next week. Bye.